This lecture is about electrical machine design, whereby the next few topics will be concerning the means by which we are able to design the electrical, magnetic, insulating, and construction properties of electrical machines, both rotational and stationary. So we will go through various aspects of design as well as design of individual types of machines. So to begin with, we will start with the principles of electrical machine design. So first off, we have various means by which we are able to achieve an engineering design of an electrical machine, whether it be a motor, a transformer, or a generator. You use these three basic principles of induction, interaction, and alignment to create all types of machines. And these are physical properties of electromagnetic fields and electric currents and voltages. So to start off with, let's look at induction, which is the first principle. Now, induction makes use of the physical property of electromagnetic fields that is described by Faraday's law and Lenz's law. So Faraday's law describes the effect of the change of a magnetic flux. So when you have a change of magnetic flux, the rate at which that magnetic flux changes, rate of change of magnetic flux, you will then have an EMF being induced or being generated by a rate of change of magnetic flux. So what does this mean? If you have let's say a magnetic field, let's call it, let's talk of a magnetic field being created by two magnets. And inside this magnetic field, you have present a conductor that is capable of carrying a current. If there is any change to this magnetic flux, you will find an EMF will be induced, an electromotive force will be induced inside your current carrying conductor. This is the basic principle of Lenz's law, that if there's any either a relative motion of the conductor or you have a change in this flux, such as might be created by an AC, if your magnets were being created by a coil with AC currents flowing through, then you would have your magnetic field, the magnitude of that magnetic field would change due to the effects of AC. So different values of magnitude in relation to time. So if you have, for example, an AC current being created there, and an AC being created there, your field would then have a varying magnitude that would in turn, due to Faraday's law, create an EMF. This is in conjunction with Lenz's law, which states that the current that is induced due to the interaction of a magnetic field and a current carrying conductor will be such that it opposes the change, it opposes the change that caused it, right? These two laws acting together help to describe the property of induction that is made use of when we are designing machines, and it is summarized in this formula. Yeah, this is the electromotive field, the EMF, is equal to the number of turns, or the number of turns in the coil, turn in the coil, and the rate of change of the flux. Yeah, phi being the flux, t being time. Okay, all you need is a changing magnetic field and a current carrying conductor in the form of a coil or a winding, and you will be able to create an EMF. So by the principle of induction, you can have three possible configurations. Either you have constant flux and a moving coil, or you have a stationary coil and varying flux, or you have both a moving coil and a varying flux, right? These are the three main configurations that make use of the induction principle. And by that method, you can then have, if you have constant flux and a moving coil, you will then create a generator. Yeah, if you think about it, if your flux is here, similar to what we have just described when we were talking about synchronous generators, you had a field in the form of a DC that was being rotated inside a stator. So in that particular case, it could be looked at as your flux does not change, but there's a relative motion between the coil and the field. So then you have a generator. Or you can have a stationary coil and a varying flux. So what would this mean? This means that your flux is changing, similar to what we had here in the form of AC, and you do not even require the coil to be moved in any way. You will simply have an EMF being induced in it by the virtue of the fact that there is an AC which has varying flux. And this is the principle that we use when we have transformers. Transformers that are used in distribution, in power supplies, and all any time where any application where you need to change the voltage of a supply. Then you also have instances where you have both the moving coil and the varying flux, and this is mainly used in motors. So either induction motors or various other standard types of motors. Okay. The second principle is the principle of interaction. And this principle makes use of the fact that we have a force being created anytime that there's an interaction between a conductor through which current is flowing and a magnetic field. And this is described by the Biot-Savart law, right? And this is a force that is created when you have interaction between a current carrying conductor and a magnetic, or we can say in a magnetic field. Actually, we still have to say in and, because it is the interaction between the two of them. So let's talk of and, right? So that force is described in the equation that. So whereby that is your force, that is the magnitude of the flux or the field density to be specific, and you have current flowing. In this case, you need a current to be flowing for the force to be present. It is the interaction between the current and the field that tends to create a force, and then you have the length of the conductor. So the magnitude of the force depends on the length of the conductor. And this is why all machines have windings that have many, many turns. That enables us to have a long length of a conductor within a smaller confined space. So you can have a compact machine with a higher amount of force. So if we were to describe this interaction, we would be able to show it in this way. So you have your magnetic field looking like that. Then you have a current carrying conductor, say looking in that direction. And because of the induced magnetic field due to the current carrying conductor, the current carrying conductor has its own magnetic field surrounding it. So that the interaction between these two fields, the existing magnetic field and the field due to a current that is flowing, you will then have a force in a given direction that will act on the conductor. Okay. And finally, the last principle of the machines is alignment. Now, alignment is slightly different from the two that we have seen before in that it relies on the properties of ferromagnetic materials. This is the principle of ferromagnetic materials, such that when you have a magnetic material, that is iron or nickel or any of these materials which tend to allow a magnetic field to be set up within them, you would then have, if for example we had a block that looked like that within that magnetic field, and that block is free to swivel in any direction, you would realize that you would tend to have the magnetic field that exists around this ferromagnetic material would bend and flow into and be set up inside the material itself. Yeah. So this distortion of the magnetic field, in order for it to be set up within the ferromagnetic material, would then create a force or a torque that would tend to move it into alignment with the existing magnetic field. And this principle is used in reluctance machines or reluctance motors. Yeah, this is purely a method of making use of the ferromagnetic properties of the machine. So you set up a machine such that, for example, the rotor can be able to rotate, and the rotor consists of ferromagnetic materials that once a field is set up around them, they will move in a way that will align themselves to the existing magnetic field. And by continuously rotating the magnetic field, you would then have essentially a motor, right? So that's the first section, principles of the machines themselves. Before we start to design machines, we need to know what are the available physical characteristics that we can make use of. Next, let's look at the design problem. So what is the design problem. So when faced with the blank canvas of creating a machine in order to fulfill a certain need or solve a certain problem, we have to take into consideration a number of elements, a number of phenomena. So first of all is technology. So in designing our machine, what principles can we make use of? So like, for example, the principles of physics that have been listed above, which is interaction, induction, and alignment. What technologies are available that make use of this? So if we wanted to design a three-phase induction motor, what are the technologies that exist? What is the knowledge that is out there that will allow us to design a machine that solves the problem that we have been allocated or that we are trying to solve? Okay. Then number two, you have what are the customer's requirements? So in the project that is allocated to us, so for example, if you your client or your customer requires a movement, say of a conveyor, or they require a pump, or they require an elevator to be built such that it does not make use of hydraulics. What are the available tools that would be able to make use of that? What is a suitable solution that would meet the customer's requirements? This would include even things like the economical constraints. What is their budget? Do they require an off-the-shelf machine, or do they have the ability to pay for a bespoke special machine? What is the environment? You know, should that machine be able to operate within a space that is risky? For example, if it is a chemical plant, you might have vapors that might be corrosive to certain materials. So you have to select materials that are resistant to that. If it's a dusty area, how would you enclose the machine, and how would you in turn cool it? Those are the requirements that we are talking about. Number three, we talk of design transfer. And design transfer means, how do we execute our design? So as you're making your design, you need to be able to make it such that a manufacturer can actually implement your design. Yeah. So there must be certain things taken into consideration. If there are certain standards that govern the type of machine you are making, those have to be put into consideration so that you can be able to communicate your design to the manufacturer or the people who will be making or implementing your design. Are there certain tools that are required? Excuse me. Are there materials that might not be readily available, or there might be constraints in obtaining those materials? Are there certain processes that would be required that would limit your ability to implement your design? So those are some of the aspects of design that one needs to consider, or the considerations that need to be made. And on the back of that, we have limitations of on the design of electrical machines. So what are some of these limitations on the design? So the actual properties that need to be taken care of when we are dealing with our machines. So first off is saturation. Under saturation, we have limits as to the amount of electromagnetic properties that we can use, and in particular, how much magnetic field can we set up within a machine. Yeah, the more magnetic field you need, the greater the excitation that is needed in order to create, for example, an electromagnet within the motor. So if you have a field winding, how much of that field winding would you need in order to create the force that we need, while not exceeding the limits of saturation? there is the magnetic circuit, the flow or the path that is taken by the magnetic field in order for it to move through the machine and interact with the current carrying conductors. That material that is used is susceptible to saturation. We have the BH curves, which we will look at, the field and the amount of density that can be set up within the materials that you have. Those are limitations that you must take into consideration. Number 2, temperature rise. Because these machines are generally machines that do work, there will always be heat losses, there will always be noise associated with that. And because of that, you must take into consideration methods of cooling. How will your machine be cooled? If it is working at the capacity that it is required to operate at, will you require special cooling? Will you require fans? Will you require water cooling? Can the insulation withstand the heat? Generally, the conductors will not likely be affected by the temperature rise. However, insulation can tend to break down, and in the selection of insulation, you need to take temperature rise into consideration. That brings us to insulation itself as a limitation. So there are various materials that can be used in insulation. We will cover them shortly. And these, as we consider them, must be must be taken into consideration in terms of the voltage gradient that they must withstand. So the purpose of insulators is to separate two current carrying conductors with different potentials, and the voltage gradient between them must not exceed the dielectric strength of the insulator itself. So for example, if you have very high voltage applications that you're dealing with, if there are generators for mains operating at 11 kV, you must design accordingly. If there are low voltage motors, small DC motors, you can also design your insulation to be lower than what would be required for a high voltage application. That has economic considerations, that has weight consideration, and that has practical manufacturing considerations. Number 4 is mechanical strength. So the physical requirements of the machine. Generally, as you have rotating machines, they will tend to spin at thousands of RPM. The centripetal and centrifugal forces that the machine is subjected to must be such that the materials that you use must be such that they can be able to withstand the forces that will be encountered by the machine during its normal day-to-day operation. That must be taken into consideration. Also, the frame must be able to support the weight of the machine. It must be durable enough and robust enough, depending on the operation environment. If it is an environment that has vibration, we must not have cracks forming within the frame. Number 5 is efficiency. This takes into consideration the conversion of power or energy. To what extent are you able to convert power from mechanical to electrical or electrical to mechanical in an efficient manner? If you need a more efficient machine, you might need higher quality materials, which would be more expensive. If you need a lower efficiency machine for a simple application, you can make smaller, lighter weight, possibly lower quality materials as required. Number 6 is commutation. This is specifically for DC machines. How would you factor in the commutation of the rotor as it is spinning, performing its work? And finally, you have power factor. This is relevant for AC machines. Power factor determines the amount of reactive power that is used in setting up the magnetic flux in AC machines. So if you require a very high magnetic flux, you would need very high reactive power, and therefore you would tend to have a low power factor. However, if your machine is required to have a high power factor closer to unity, such as induction machines, you would need to take that into consideration and possibly design such that you have lower flux densities than what is possibly being achieved by a machine. So now let's look at what are the actual design areas that we must use, the design areas that we need to design for when we are dealing with electrical machines. So these are the main areas. If you have your machine that has these are the main areas that you would need to take into consideration. So the first of these is the magnetic circuit. Definitely, the very principle of electrical machines requires you to have a magnetic circuit and an electric circuit. Both of these must form part of the components of your machine. So generally, your magnetic circuit would be the frame or the yoke or the mountings of which the windings must be put onto that allow magnetic field to be set up within them. Usually these are made of ferrous materials or materials that have a low reluctance and enable the magnetic field that is required to interact with the electrical currents to be set up within those materials. Secondly, you have the electric circuit. So these are the windings within the armature and the field, the actual conductors that you're talking about. So these are conductors and windings that need to be set up within your machine. And your magnetic circuit would be your yoke for your windings and various laminations, or the core in which magnetic circuits are set up. Next, you have insulation. So there are various types of insulation which we will go through. You have to protect the electric circuit. Windings consist of conductors that have to be separated from each other, otherwise you will have short circuits, and insulation form a part of that. Also, the windings need to be insulated from the core and also from the frame, and they must be safely able to be connected to the outside power supply or the load. That's insulation. We also need to have heating or cooling or ventilation of the machines. These are a natural aspect of any machine that is performing work, as we had mentioned before. Vibrations, energy losses, and such like need to be taken into consideration so that you don't damage the machines themselves. So it has to be designed into the properties of the machine. And finally, the mechanical construction. So the machine needs to have a frame, supports, bearings, and so on and so forth. All materials that have to be properly designed and included within your machine itself, right? So these 5 elements constitute the design aspects of electrical machines that we shall be looking at in the next few lectures, right? So we will look in turn at the magnetic circuit, the electric circuit, a bit of insulation, heating and cooling, and some of the mechanical construction. But we will spend quite a bit of time on these 2 main components, the magnetic and the electrical, right? So those are the main elements, the main aspects of design of machines. And so we will now move next to the materials that are used to design machines.